So what we're looking at is we're going to look at part 4, which is the ideal gas law and atmospheric pressure. And what you're going to find here is that in gas systems, it always moves from a high pressure region So if I have a high pressure region, it's always going to move towards a low pressure region. That's not the way you spell pressure. So systems will always move in that direction. And in today's lab, you're going to find that in each situation, the high pressure is always the same. The high pressure is always going to be atmospheric pressure. Your goal here is to determine how the low pressure, came to be. And the way we do this is we use, so the law that we're going to use here is that we're going to use the ideal gas law. So the ideal gas law is a very simple, naive model of a material. And what you'll find here is that the importance of the ideal gas law is that that an ideal gas is the simplest possible material to understand. And the key thing about the ideal gas law is that there is no bounding between gas molecules. So in essence, if you talk about air, which is nitrogen and oxygen, that's not really an ideal gas. However, we can treat it as an ideal gas if the gas is rarefied, which means that they don't interact very much. And then it becomes an approximate model of an ideal gas. That being said, we don't want to use the ideal gas law as a calculational thing, but more of a conceptual thing. And this is what the ideal gas law says. By the way, there is no such thing as an ideal liquid model. There is no such thing as an ideal solid model. And the reason why is because liquids and solids, they have binding energies, and these binding energies vary from liquid to liquid as well as solids to solids. But if you have an ideal gas that has no bonding, then the only thing that describes the ideal gas is its kinetic energy, if you think of it from an energy viewpoint. So here's what we know. So the ideal gas law essentially says this, that the pressure of a gas is caused by colliding gas particles with the walls of a container. And so that means here that then the ideal gas law then says the following thing here. It says that the pressure of this gas is proportional to three things: the number of gas particles times the temperature of the gas divided by the volume. This is effectively what the ideal gas law tells us right here. So what I want to do here is that I want to show you an applet. And I'll share my screen to actually do that. Well, it's here apparently. So here's an image of a gas simulator. And the first thing that we want to do here is that we want to make the gas particles as small as possible. In the ideal gas model, the volume of a gas particle is 0. So if I come in here and I now start pumping, gas molecules into this container, the fact that you can see the gas molecules tells you that this is not really an ideal model. So you're seeing that there's collisions within the gas, which is not an ideal gas. However, how we define the pressure of this system depends on the collisions with the boundary of this container. And you could see that there are a couple of things that we can measure here. One, we could measure the pressure here with this gas gauge, and here it's measured in atmospheres, but we can also measure it in kilopascals here. So that would be the metric system. And another thing here is that we can change the volume by moving this container. We can change the temperature by either adding heat or removing heat from the gas. And then finally, we can open this guy to let particles and then change the distance here. So what I'll do here is that we do have a collision counter. And if I run this, this tells me how many collisions. If there's more collisions, then the pressure is higher. If there's less collisions, the pressure is lower. So let's look at the first thing that we want to look at here. So if I come back here and I go back to my sheet here, I'm going to say the following thing. So the first thing that I'm going to do is that I'm going to look at the number of gas particles. So what I would expect here is that if I have a smaller number, then I would expect less collisions with the walls, which then tells you that I'm going to have a lower pressure. On the other hand, if I have a larger number of gas particles, then I should have more collisions, and therefore I should have a higher pressure. Let's go look at this with the applet. So here's the applet. So now what I'm going to do here is that we just ran this thing, and let's see if we could talk about the number of gas particles. So right now, the number of gas particles you can see right here are 338. So what I'm going to do here is that I'm actually going to take a screenshot of this. Can I move this over here? Will this allow me to do that? Nope, it doesn't. So I'm going to take a full screen of this guy right here. And then I'm going to put this into my OneNote so that I have it, and then we can compare the two things here. So, okay, I've now captured this thing. So now what I want to do here is that I'm going to change the number of gas particles. How am I going to change the number of gas particles? I'm going to let them out. And you could see that the gas particles are dropping. You see that number. Now let's close it. Now look at the wall. Now I'm going to do the collisions with the walls here. And you could see the collisions with the walls is lower. So if I look at this guy, what am I actually seeing here? So now I want to come back and I want to compare what we just did with the other one here. So let me add this to my sheet here so that we can actually look at that. Now, let me go back. And I am on screen one. So this right here, if I make this a little bit smaller, this is where I had a large number of gas particles. And where do I see this at? Where I see this is that I see this right here. So if you look at this, the number of gas particles here was 338. Now, let's talk about wall collisions. So when I look at the wall collisions, you could see that the wall collisions right here are equal to 625. That's how many collisions. Because of this, you're seeing here is that now the pressure in this situation, you can see is right here. So the pressure in this case was 400, let's say approximate this to 4,000 kilopascals. Now, let's look what happens next here. According to what the image that we just showed here, I could then come back and I could start looking at the same values here. Right? And I think this is, this is going to be blue, and then this guy's going to be orange. And what you're seeing here is that now I have a small number. And what was that small number? It tells me that it was 170. And then I then talk about the number of collisions. And we could see that that number is 238. And then finally, if we look at the pressure, in this case, the pressure now is around 1,200 kilopascals. You can see here that if I have a smaller number of particles, I'm going to get less collisions, therefore lower pressure. But if I have a larger number of particles, then I'm going to have more collisions, and I'm going to have a higher pressure. So that tells us about how pressure behaves on that. Now, the next thing I want to talk about is I want to talk about temperature. So when I look at temperature here, what just like we talked about over here, we want to look at this thing here. So what happens when you have temperature here? So here's what we know. If I have a lower temperature, that means I have slower particles, slower gas particles. And if I have slower gas particles, that means I'm going to have less collisions with the walls. And as a consequence, I'm going to have a lower pressure. On the other hand, if I have a higher pressure, higher temperature, they're going to be moving faster. And if they move faster, the walls are going to experience more collisions. So then I'm going to have a higher pressure. Let's go look at this with the applet now. So when I look at this thing, what am I actually seeing here? What I want to do here is that I want to increase the number of particles. Let's say that we're about the same, which is around 320. So now what we want to pay attention to here is that look at the walls of the container here. The walls are experiencing 200. No, let me run this again. So I get a value here. And so what you're seeing is that there's 478 collisions. And I'm going to keep the number of particles fixed. So now I'm not going to change the number of particles. So the only thing I care about is really just what is the pressure, what is the temperature, and what is the collisions. So let me copy this guy right here. And I want to know what the temperature is in this situation. So now that I've copied this.
Carlos,
Yes.
you didn't switch. Oh, never mind. I think you switched around. No.
Are you seeing the applet?
No, I think we're seeing like your image copy paste area.
Okay, let me go back. Sorry about that. Too many damn windows.
Yeah, we're looking at your
Okay.
image editor.
Is this it right here?
Yeah.
Yeah.
Okay. So all I did here is that I ran the wall collisions. I don't care about the particles because I'm going to keep them fixed. So I see the pressure and I see the temperature. Now I'm going to use this little guy here and I'm going to heat this guy up. So as I start to heat up the gas particles, you can physically see that they're moving faster. Actually, I wonder if this guy shows me speed. Nope, it doesn't. Does the stopwatch show me speed? Nope. Anyway, I'll just leave it right there. But you can clearly see that this is a higher temperature and they're clearly moving faster. So now if I run this again, let's compare these guys. So now let me copy this and let's go back to my OneNote. So now let me go do a new share. And I want to go to screen 1. So let me insert this guy here. So are you seeing my OneNote now?
Yes.
Okay, so let's look at this guy here. So the first thing that we want to do is that let's look at what the temperature is. So compared to the second temperature, you could see that this temperature here is 738 Kelvin. This guy's 182. So what I could say here is that this is a low temperature. So when I look at this low temperature here, you're seeing that I have 182 Kelvin. Now, if I look at the collision rates, so then if I talk about the number of collisions, I could then come in and say, this guy is 478. So now, finally, we need to look at the pressure here. So then if I look at the pressure, I'm going to find that this guy roughly is going to be, let's say, 2,300 kilopascals. Now, if I compare the same thing here, there's this guy, and I have that guy, and then this one here, we clearly see, if I now copy this guy, and I just bring this guy down here, and if I just modify this a little bit, we could then say that I have what? That I have a high temperature, and this high temperature here is 738 Kelvin. The number of collisions here is 926 with the walls, and the pressure now reads around 9,300 kilopascals. So you could, if I compare these, you can see here, if I make this just a little bit smaller, that the key things here is that by looking at the temperatures, we can see that it really tells us how those pressures are going to behave. Okay. Now, the last one that we have to deal with is the volume. And what we see with the volume here is that up here, the ideal gas tells us that the volume is inversely proportional to the pressure. So if it's inversely proportional to the pressure here, then if I have a large volume, what we're going to find here is that I'm going to get less collisions because particles travel farther. And if I have less collisions, then I'm going to have a lower pressure. On the other hand, if I have a smaller volume, then I'm going to have more collisions because the particles travel less. They travel less before a collision, and as a consequence, this will be a higher pressure. So what does the applet say here? So let's see if I get the right window this time. Okay, there we go. So now let's add the volume here. So let's let some of these gas particles out because there's a lot of them. So let's reduce this a little bit. Actually, I'm going to have to reduce this a lot because I'm going to So now let's take an image of this so that you could see what I'm talking about. Okay, so I got a copy of this, right? No, I did not. Okay, now I did get a copy of it finally. So now what I'm going to do here is I'm going to change the volume. Okay. So what I want to do here is that I want to reduce the volume by, let's say, let's see if the pressure is, let's say about that much. Actually, I'm not going to blow this out. Let's go to half of it. Yeah, that's better. So now what I'm going to do here is that I'm going to, I didn't run the collisions. Damn it. Okay. This is the collisions with the wall. So let me go and copy this. Okay. This is with the volume, the width of the volume being 5 nanometers. Okay. Now I got to go all the way back out to 10. Okay. Now I'm going to run this guy again. So you could see that the volume here is different this time. Okay. I'm having trouble with too many windows. Here, give me a moment. And then I need to capture this guy. Sorry about the delay. Okay, I think we're good now. So here's my final screen here. So here's what I have right here. If I compare the volume, you could see in this situation, I have a smaller volume. And because I have a smaller volume, I'm going to have, and this smaller volume, I'm going to call this guy, just the width of this is then going to be 5 nanometers. Now note, I'm not talking about the area of the container, just the width of it. As a consequence, you're going to see that if I look at the number of collisions, this number is 605 collisions. So then if I look at the pressure, you see here that the pressure in this case is around 6,700 kilopascals. Now, if I do the exact same thing when I increase the volume, what do I see here? And then instead of a smaller volume, I have a larger volume, right? So if I come in, I see that this is 10, this is 412, and then finally, this is this pressure. So if I start to look at these values, you're going to see that the number of collisions is 412. The pressure here is going to be around 33, 50 kilopascals. So if I compare these two, you can see here that the volume being smaller has more collisions, a higher pressure, right? So the ones I'm comparing is that I'm comparing this guy and that guy to this guy and that guy. So you could see that the inversely proportionality seems to be working out. So that being the case, you have 4 parts. And the thing that you want to pay attention to is this here. So when you go to do the parts of the lab, you want to look at this guy right here. this is what we were talking about. Our picture here is that can you identify how the low pressure was created? Oh, I realize this is too small. Can you do that? That's the whole goal here of this lab. So you're going to see that there are 5 parts. So if I look at now part 4, the first one here, A, you have steam in a can. And you're going to boil a little bit of water, and then you're going to put it into some cooler water or ice water to see what actually happens. How did the atmospheric pressure do to that low pressure region? The same thing happens with the suction cup. The suction cups are a little bit tricky here. And the one thing you want to pay attention to, and this is the hint, is the volume. And then when you look at C here, you're going to be looking at the Magdeburg hemispheres. And this one will be quite obvious as how you create the low pressure. And then if you look at D here, I think this one will be the same thing here, is that you're going to be looking at a balloon in liquid nitrogen. And this one is tricky. This is what's called the inside outside balloon. And you want to think about this is that you know atmospheric pressure is at play. That's a tricky one.